we were discussing about the importance of the geometrical shape of the rigid body, which is we are having this rigid body and its geometrical shape and its influence on the mass moment of inertia matrix. So we considered three cases. First one is the body possessing just a one plane of symmetry, and for which we showed that the direction, right? So for which the direction which will be normal to this plane of symmetry, and you know that if the xy plane is the normal, is the plane of symmetry, then if it is xy plane, then we know that the z axis, it will be normal to that xy plane, and as a result we see that all moment of inertia terms in the mass moment of inertia matrix, all terms involving z will be 0. For example, in this case we had xz plane of symmetry, so naturally y will be the normal to it, and all mass moment of inertia involving y terms are 0. That was okay, fine. The problem starts here. Just a moment, someone is knocking the door. Let me give him the admission. So you see the second case, it was the case of the body possessing two planes of symmetry. So it is having only two planes which are perpendicular to each other, and those two planes are the planes of symmetry for the body. You can think of many geometrical shapes which are possessing two planes of symmetry, correct? So in such situations, what will happen? Now, for example, let us show. Yes. So, so we see that if we have two planes of symmetry for a body, so what we have, let us see that this is one plane of symmetry and this is another plane of symmetry. And the two planes of symmetry intersect each other along a line. So this is this red line, which is the line of intersections of these two planes of symmetry of the body. And then what we have, we say we take any point on this line and erect the two more lines which all of them are mutually perpendicular to each other. So what we are doing, basically, we are taking this line of intersection of the two planes of symmetry, and we take anywhere on this line a point, and what we have, that at that point on this line we erect two more lines such that you know that all of them are mutually perpendicular to each other. So this is what one line is along this plane of symmetry and another line is this plane of symmetry. So we consider these two lines which are on the planes of symmetry that body possesses, correct? So you are having one line which is lying in one plane of symmetry, and you are having another line which is lying in the second plane of symmetry. So now if I see, so if I now consider, so if I make these two lines little bit thick and red, so that you can understand they are, let me see, just a moment. Oh, এটা group হয়ে গেছে, sorry. So what we are making, this line we are making it red and we are making it little bit thicker. So let's say this is thick, and we take the format of this and make this other line also like this. So basically the three red lines, they are constituting three sets of rectangular coordinate axes. And you see, if we, for example, consider this to be an xy plane, a plane, this plane, if we consider this to be an xy plane, right, and this we consider as to be the, say for example, yz plane, then what will happen? If it is xy plane, then the z axis will be normal to it, and if it is an xz plane, then y axis will be normal to it. So this will be z axis, this will be y-axis and this will be x-axis. For example, let's say we arbitrarily take this so that they constitute a right hand triad, etc., etc.
স্যার বলছি যে ওই ইয়েটা ভার্টিক্যাল প্লেনটা xy।
হ্যাঁ, মানে তুমি যে কোনো একটাকে ধরে নাও যাতে রাইট হ্যান্ড ট্রায়াড তৈরি হয় আর কি। সাপোজ এটাকে যদি আমি xy say if it is xy plane, right? If it is xy plane, and then if we call it as the xz plane, or if you call this as the xy plane, this is the xz plane, rather it will be better, then it will constitute the right hand triad. So I call this as the xy plane, this horizontal plane, xy plane, and call this vertical plane as the xz plane, correct? So if it is xy plane and this is xz plane, then their line of intersection will be the x-axis, this red line, right? And then if it is xy plane, then perpendicular to it will be the z-axis, so this will be considered as the z-axis. And if it is, you know, if it is this xz plane, then perpendicular to it will be considered as the y-axis. So if I now take these three lines, correct, then about these three lines, all the mass moment of product moment of inertia, all the product moment of inertia terms of your inertia matrix will be 0, correct? Now at that, on the last day, in a hurry and over enthusiastic way, I commented that if I take many other two lines, for example this line and this line, and also this line, which such that they are also mutually perpendicular to each other. That means if I rotate this red line and this red line in a plane which is, you know, parallel to this plane, I mean to say this is x, I said this is xy plane, I said this is xz plane, and then naturally the other plane will be xy plane. So this two, if I rotate in that plane, then we have another sets of axes. This is one, and this is one. And I said that they also will be the, you know, the principal axis of inertia at this point, which is wrong. This will not be correct. So if this will be true in a special case, that case will be coming later. So we see in the next step, we will be coming to that special case. So if it is a general case of a body which is possessing these two planes of symmetry, in that case, these two lines along with this x-axis, they will not constitute what is called the principal axis of inertia. On the other hand, this line, this red line, and this red line, they will constitute the principal moments, principal directions or principal axis of moment of inertia about this point on the body. Now if you go on selecting different points on this line, go on taking different points on this line, there you will see that all the cases, at that point, those will be the principal axis of inertia. What I mean to say is this: for example, if someone chooses a point here and erect a line in this plane, right, in this plane which I called it as the, say for example, which I called it as the which I call it to be the xz plane. So I take any point on this line and then take another line on this horizontal plane, which I called it arbitrarily as the xy plane. Then I will again have this axis, and this axis at this point. Again, they will be the directions of the principal axis of inertia at this point. But if I rotate these two axes, if I rotate these two lines with respect to this line at that point, as for example, here we have rotated this red line and this red line about this line at this point and came to this axis and this axis, then this three sets of axes, I mean to say this one, and this one, will not be the principal axis of inertia at this point. It will be true in a special case. What is that special case? Now that special case is our third case, which we considered as the body to be axisymmetric body or rotationally symmetric body. You know, this rotationally symmetric body, I told you that the body is generated by revolving a particular, the area about this line. For example, I considered this curve and this area, and I considered this axis. Then I revolve this area about this axis 360 degree, and I will generate a body of revolution. Remember, in your engineering mechanics class, in statics class, you solve some problems like Papas-Gouldina's theorems involving such bodies of revolution to find out the volume of the body. So such case, you see that this body will be generated in this manner. For example, the body I showed, try to show it here, though the figure is not very correctly drawn because it is drawn in freehand. So in this case, this body will generate a shape, something like this, which someone called me that whether, sir, it is the cooling tower shape. I said that it is not the cooling tower, but the illustration is very good, that because the cooling tower, if you see any cooling tower, then you will see its geometry of the cooling tower is almost pretty similar to this type of shape, which is known as the hyperbolic shape of the cooling towers. Anyway, so this is the case of the, an example of body of rotationally symmetric body. You can consider a right circular cylinder to be an example of rotationally symmetric body. You can consider a right circular cone to be also the, the body which is axisymmetric body. So in such cases, what we find that, suppose for example, if I assume that this is the axis of symmetry, this z-axis, I take this axis of symmetry as the z-axis, okay? So if I consider this axis of symmetry as the z-axis, then if we take any two lines, because the cross section of such body will be always a circular one, because it is generated by revolving this entire curve or entire area about this line. So naturally, you see the cross section will be like a circle. So on that plane, if I draw two perpendicular lines like x-axis and y-axis, then this, because of the circular symmetry, the ixx and iyy, these two will be equal. So the mass moment of inertia of the body calculated about the x-axis, calculated about the y-axis, will be both equal to each other because of the, which is known as the rotational symmetry, correct? So if you consider the case of a cylinder, you will find it. If you consider the case of a right circular cone, you will find it. Or if, for that matter, if you consider any rotationally symmetric or axisymmetric body, you will find that. Now, since this body has got infinite number of planes of symmetry, because of the circular cross section, you have infinite number of planes of symmetry. As a result of this infinite number of planes of symmetry, what you will find there, in that case only, suppose if I now consider, you see I have here shown only two planes of symmetry. Now imagine I am having infinite number of planes of symmetry like this. And this line represents the axis of rotation, which we took as the z-axis in our previous illustration. So if this line is the axis of symmetry, and then if I go on taking different points on this line and go on taking different lines which are mutually perpendicular to all each other, then they will represent the product, I mean to say the directions of the principle of axis of inertia at that point. That means what I mean to say, for example, if this is a rotationally symmetric body possessing multiple planes of infinite number of planes of symmetry, then at this point, this one will be the planes axis of, I mean to say the directions of the principal axis of inertia at this point. And not only these three lines, but also if you go on taking the lines like this, I mean, say you rotate this line in this plane and you obtain another set of lines like this and this, then this line, and this line will also have the same directions of principal axis of inertia at this point. So if you go on taking these lines, go on rotating these two lines with respect to this axis, all the lines that you will be getting, they will be forming the what is termed as, because
Excuse me, sir.
it is basically rotating in a circle. Bolo. কিছু বলবে?
হ্যাঁ স্যার বলছি অরিত্র আর ওই
এরা ঢুকতে চাইছে?
আদিব আক্তার
ও
ঢুকতে
আচ্ছা
পারছে
আচ্ছা
অনেকক্ষণ ধরে ওরা ট্রাই করছে।
হ্যাঁ ঠিক আছে ঠিক আছে ঠিক আছে okay okay so you see therefore that if I now actually now this rotation is basically taking place along a circular cross section. If I draw this, try to draw the circular cross section here, I'll like to explain this thing to you. So you see all these lines, all these rotations will be along this circular cross section. So if I just draw a circle over here, this rotation bhalo dekhate pacchi na ekhane chhede dieta. So you see all these lines are rotating in a circular path here with center at this point. So in that circular section, if you go on taking the different lines which are mutually perpendicular to each other, they will be forming what is termed as the the directions of principal axis of inertia at this point. So in this geometry, so if I summarize the geometrical shape, then we see from here that if the body possesses a single plane of symmetry, then we will be having, for example, if the plane of symmetry is the xz plane, under such circumstances you will find that all the the product moment of inertia terms will be all the product moment of inertia terms involving the normal to this plane will be 0. Then for example, if I have two planes of symmetry, then all my product moment of inertia terms will be 0. All these six terms this in this case will be 0. All these six terms will be 0. On the other hand, if I have the rotationally symmetric or axisymmetric body, in such case, just a minute, I just align this portion page for our view. So if we have the rotationally symmetric body, then you find that all our product moment of inertias are not only 0, but also the two axes of inertia, the two mass moment of inertia will be equal to each other. For example, in our previous case, so if I come back to our figure, imagining that this represents an axisymmetric body and imagining that this represents the z axis, I mean to say this line is the z axis, then the other two lines may be called as the x axis and y axis. Say for example, this line can be called as the x axis, this line can be called as the y axis. So this moment of inertia, mass moment of inertia about these two lines at this point, not only at this point, it will be true for any other point on this line, on this z axis. These two mass moment of inertia terms will be equal to each other, and all the remaining product moment of inertia terms will be 0. So it will be the difference between the rotationally symmetric body and a body which possesses two planes of symmetry. In case of a body which possesses two planes of symmetry, we find that all the six terms of the product moment of inertia are 0, but none of the mass moment of inertia terms are equal to each other. On the other hand, if it is a rotationally symmetric body, like the previous case, all the six terms of the product moment of inertia will be 0, but any two of the mass moment of inertia values, I mean to say x, y or z, any two of them will be equal. কিভাবে সেটা ইকুয়াল হবে? For example, if the z axis is the axis of revolution, then ixx and iyy terms will be equal. Suppose you take the axis of revolution to be as the y axis, for example, in that case ixx and izz terms will be equal. Suppose someone defines the axis of rotation as the z axis. For example, in our class note we had defined this axis to be the z axis, this axis of revolution. We had defined this to be the axis of revolution, z. So in this case, ixx and iyy will be equal, and all the remaining terms of the inertia matrices will be 0. So therefore, this is one classical example of how your geometry is affecting your inertia matrix. Now we consider the next special case, which we call as the thin plate or slab-like body. In case of a thin plate or slab-like body, what happens? Any one dimension of the body is very, very small in comparison to the other dimensions. For example, this is a slab-like body, and this dimension, suppose I set 3 axes, coordinate axes like this. We take at the middle plane of this plate-like body, inside a point, an arbitrary point we take, say O, and at point O we erect these 3 sets of axes, X, Y and Z. So this is at the middle plane or mid plane, mane passing through half the thickness of this plate. Suppose if I consider that plane, mid plane, that mid plane you can consider, and you see this is X axis, Y axis and Z axis. And this dimension along the Z direction is very, very small. So if this is a very thin slab-like plate, I can imagine that this body is symmetric with respect to this mid plane, right? This mid plane. This is symmetric with respect to mid plane. That means top half and the bottom, top surface and the bottom surface, these 2 areas, you can consider this is an area, and at the bottom also you can consider this is another area, plane surface area, top surface area and the bottom surface area. Both of them are symmetric about with respect to this mid plane. So I can consider the XY plane as to be our plane of symmetry, and quite naturally anything involving Z, any product moment of inertia terms involving Z will be equal to 0. So I have therefore, you see from here, this any term involving Z will be 0. So you see this IYZ and IXZ will be 0. Why it is 0? It is because that the XY plane can be considered as the plane of symmetry, which is passing through the mid section of this slab-like, thin slab-like body. Not only this product moment of inertia involving Z, which is normal to that plane of symmetry, will be 0. This is a case like case 1 we studied, where we analyzed the body possessing a single plane of symmetry. So this is an example where we are considering this to be possessing a single plane of symmetry. So in that case, the term containing the product moment of inertia term containing the Z will be all these terms will be 0. So IXZ 0, IYZ will be 0. Not only is that, if I consider, suppose for example IXX, then IXX from the definition it is written like this. Now since the dimension about the Z direction, along the Z direction is very, very small in comparison to the other dimensions, so this can be approximately expressed as y squared dm. So Z can be taken to be 0. In a similar manner, we can say that this was the case of IXX. In a similar manner, we can write YY to be also equal to, you know, this is also equal to approximately equal to x squared dm. If I neglect this x square, the z square contribution, neglecting the z square contribution, we find this is 0. So as a result, you see, if I consider IZZ term, on the other hand, if I consider IZZ is nothing but integration over the mass m x square plus y square dm. And we find that IXX is equal to integration y square dm and IYY is equal to integration x square dm. So it is quite simple to note that IZZ is nothing but it is equal to IXX plus IYY. So this is known as, this particular result is known as the perpendicular axis theorem, which is only valid for a slab-like body. So in case of a cylinder, if you think of the case of a long cylinder, in the case of long cylinder, you will never find that, you know, that you will never find that IZZ, say if this is the z-axis for the case of a cylinder, if I imagine that this is the z-axis, then IZZ for a cylinder will never be equal to IXX plus IYY. On the other hand, if you make the cylinder compressed in the direction of z-axis, তুমি যদি সিলিন্ডারটাকে compress করতে থাকো along the direction of z-axis, then the long cylinder will ultimately come down to a form which is like a tablet, একটা ট্যাবলেটের মতন কয়েন শেপের একটা জিনিস চলে আসবে। So it is like a circular coin or a circular plate which is having very small thickness. So that you may consider as a circular disc. And in case of circular disc, definitely the perpendicular axis theorem will be going to be valid. So therefore, you have to understand, this is a very important thing. People often make mistake applying the perpendicular axis theorem for a long direction body, but it will never be true in case of long direction body. It will be only true when the body is having a very small direction about the perpendicular axis. For example, a plate-like or a slab-like body. So in case of a slab-like or plate-like body, we have this particular thing. So you see from here, we note that, again we come to this thing, we note that IYZ and IXZ terms were 0, but IXY is in general not equal to 0. IXY is in general not equal to 0 unless the plate is having a plane of symmetry. For example, if we have a circular disc, in that case, definitely, you know, this plate has got many planes of symmetry because it is circular, many planes of symmetry. So in that case, all the product moment of inertia terms will be 0. But if you, instead of taking a circular plate, have you taken a triangular plate, an isosceles triangular plate, or a, say, for example, a scaling triangular plate, একটা যে কোনো একটা triangle নিয়ে তুমি একটা triangular plate তৈরি করলে, in that case definitely you will not find all product moment of inertia terms will be 0. Only those product moment of inertia terms involving the direction to the normal to the plane of symmetry, those terms will be having 0 contribution. For example, if we consider Z is our normal to the plane of symmetry, then the product moment of inertia involving the Z terms will be equal to 0, but the other will not be equal to 0. But if it is a symmetric case, for example, a circular plate or a rectangular plate or a square plate, all of them, you know, will be having all the terms of the product moment of inertia will be 0, because the x-axis and y-axis itself is also representing the you know, they are forming the planes of symmetry. As a result, those terms IXY, they are also will be equal to 0, because then the body possesses more than one plane of symmetry in this case. So for a rectangular plate or a square plate, the body will have more than one plane of symmetry. As a result, all the terms of the product moment of inertia will be 0. Now there is an interesting thing. For example, in order to find out the contribution of the mass moment of inertia, what we are doing, we are isolating a differential area on the top surface of the body, and let us say consider a small cylinder object. That means we construct a small cylindrical shape of which the cross section is the small area which is visible on the top surface or maybe visible at the bottom surface as well. So I can say here the area dA is enclosing a differential volume, and how much is that differential volume dV? That we can write it to be equal to how much? Now T multiplied by dA. So T, which is the average, you know, the uniform thickness multiplied by the cross sectional area dA. If we imagine, of course, the body is having uniform thickness. If the thickness, again the thickness can vary. If the thickness varies, then we cannot write this simple equation. But if the body is possessing uniform plate thickness, then of course we can write this dV to be equal to TdA. Otherwise, we can write dV to be equal to T into dA, and the T can vary. T can vary in the Z direction. Okay, so under such circumstances, we can write that dV can be written as dA into T, and IXX can be therefore written as, say for example, I take the case of IXX. So I write that it will be integration over the entire mass domain y squared dm, and in place of dm, what we do? In place of dm, we introduce this term, that is rho into T into dA. And as I said that if T varies along the Z direction, then this T can also be, then this T will be variable of integration, right? And if I therefore say, what I write now, if the body is assumed to be homogeneous, So please see, the body is homogeneous and the thickness is uniform. So if I assume these two assumptions, if we take these two conditions, the body is homogeneous and the thickness is uniform, then this rho and t, they will be both treated as constants with respect to integration. So they can be taken out of the integration sign, and the integration will be only performed like this. So the integrand only will be y squared dA over the entire area. And you know, this integration over the entire area y squared dA is nothing but area moment of inertia, second moment of inertia about the x-axis. So I define the second moment of inertia here by the symbol J, because we have already used to designate the mass moment of inertia. So let us suppose that if Jxx represents the second moment of area about the x-axis, then Ixx, that means the mass moment of inertia and the second moment of inertia, these two will be related by this simple equation, where you can see it is written as Ixx is equal to rho into t into Jxx, or which I defined as alpha into Jxx, where alpha, which is equal to rho into t, is nothing but mass per unit area. So it is a physical physical property of the body, the mass per unit area, and that therefore I can say the mass moment of inertia and the area moment of inertia will be proportional to each other for a slab-like body. In a similar manner, I can write from here. So in a similar manner, I can say that in a similar manner, I can say that Iyy can be written as alpha into this, and Izz is written as alpha into Izz, right? So this is our basically, the chapter where we try to show you the the case of what is termed as the mass moment of inertia, and its it is actually discussed in independent of any mechanics involving it. In any mechanics involving it. We do not know how this mass moment of inertia chapter is going and coming and fitting to us, correct? We do not know yet, but you know that how these terms will be coming into our picture, that we can come and discuss in our next chapter, which is termed as, this is you can consider as to be the what is called as the first chapter of our study of advanced dynamics of rigid bodies. So that chapter is basically called as the angular momentum. So this angular momentum chapter, that means here the angular momentum will play a very vital role. Why we say that angular momentum is playing a very vital role? Because we see that so because we see from here that just a moment, angular momentum, just a moment, I open up the application. কারণ আজকের ক্লাস তো খুব ছোট, আজকে আমাদের তাড়াতাড়ি করে নিতে হবে। So you see that the case of angular momentum. So how we are going into discuss this angular momentum? Why the angular momentum is so important? Because the angular momentum takes care of the what is called the mass distribution of a body. Say this is a rigid body, correct? So this is a rigid body. How the angular momentum is coming into our dynamics, that we will discuss later. But suppose that this is a rigid body that we are having, and first let us define what is meant by the angular momentum of this rigid body. So for that matter, again we are taking a point here. So this point, angular momentum about a point, it's only angular momentum is a vague thing. What you need to see, that angular momentum about a point. So what we are going to say therefore, so let's see that we are having a point, and that point can be anywhere on the body. So it may be within the body, it may be outside the body, whatever. So let's say this is a point which I consider as the reference point. So since this is a reference point, I mark it with a red color. So this is the reference point that we have. Now let's take any arbitrary point within the body. So this is an arbitrary point. And we know that because of some motion, this body is having some dynamics. As a result of that dynamics, this point is having some velocity. So let's say this is the velocity direction. So this is the velocity direction, correct? This is the velocity direction. Now, if this point, suppose, for example, we consider that this point is having the mass dm. So we have the mass here, that is dm here, concentrated. And this velocity, we can therefore say that we have some velocity over here. Now, this reference point that we have taken inside the body, we take it inside the body, and we first, let us say, then what we try to see from here, that I need to have, first of all, a position vector of this point. Say this is the position vector of this point, differential mass, which is having some velocity, say v bar. Then how we can define, if I suppose that this position vector, please write it in your khata, if this position vector is represented by r bar, and if this velocity I write it as v bar, then how we define the angular momentum? So angular momentum, small angular momentum, that means for this mass we can say the angular momentum is dh. A is suppose that point, red point, the red point take ami nichi reference point hisebe. Let us suppose that this is our red point and we call this is a vector quantity. So I write dha bar, that will be equal to how much? Now that is equal to r bar. So we take r bar. R bar, you see, as I told you, that it represents the position vector. R bar sorry, this is r bar cross, we have, this is v bar. V bar, what is v bar? V bar representing the velocity of that differential mass point, and we have the differential mass attached to it. So this is what is, the defined as the angular moment. I'm again coming to this. Say this is a body, rigid body. This is a point, reference point. I call this reference point designated by the symbol A. I take any arbitrary point here. The black point is any arbitrary point within the domain of the body. I said this point A can be arbitrary. It can be here within the body. It may be lying outside the body as well. No problem. So only thing what I have to do is I have to take this differential mass. Say this point is having some mass. This mass I call it to be dm. And because of the motion of the body, how the motion is coming, etc., I am not coming. But because of the, suppose this body is in motion, because of this motion, this particle, mass particle is having some velocity. Instantaneous velocity vector is this one, v bar. And then I can say the angular momentum of this mass particle about this point will be equal to the cross product of the position vector of this point with respect to this point, which I define it as r bar. This cross the linear momentum of this point, that means the velocity vector multiplied by its mass. So this is how I can say, this is how I can write the angular momentum in the differential form. Then what will be the angular momentum about this, total angular momentum about the point A? Then it is definitely, say, I copy it, Control C, Control V. So we therefore find that this, how you can write it equal to here? So we simply need to integrate this equation. So what we need to do is simply to integrate this equation. Say, let's say we use this integral form, and within the integral, the integrand rather, the integrand will be this one. So I copy and paste it here, and this integration has to be performed over the entire domain. So forget this upper limit. we don't have any upper limit here. This m, I show it to designate that the integration has to be performed over the entire mass. So you see, therefore, this is how we can write this expression. So we can say from here that it is equal to what? So we can write like this. We just copy and paste it. You please write it down in your khata. So you see that your V bar, how we can write this V bar? Now this V bar, I can say, if you recall your study of kinematics in your first in your previous semester. In your previous semester, we discussed in detail the kinematics of rigid bodies, three-dimensional kinematics of rigid bodies. So I therefore express this velocity vector in terms of another point which we call as the center of mass. So you see that we have this body, and let us take, suppose, this point. This point we color it in a different color and shape fill, just to show you this is something special. This black dot, this represents the center of mass of this body, correct? So this, suppose this is here, this is here. Suppose this center of mass is there. Now the center of mass of the body is having some velocity. So it is also having some velocity. Suppose that instantaneous velocity of the center of mass is in this direction. That means when this point's velocity is in this direction, at that same instant, the center of mass's velocity is in this direction. Then we just consider two more position vectors. One is this position vector, another is this position vector. Another is this position vector. And I color them. Say this one I call it as a, I make it a dot, and this one I color it with this one. So you see that the original position vector is now broken into two position vectors. I call this position vector, I call this position vector as R bar. I call this position vector as R bar, because this represents the center of mass. So center of mass mane hocche position vector, I call it as R bar, and this position vector we call it as, say, rho bar. I call it as rho. So this is R, this position vector was R, this is R bar, and this is rho. So I am again calling this is R, this is R bar, and this is rho. So what I can therefore say, in place of this position vector, now I can replace it by, কিভাবে আমরা এটাকে রিপ্লেস করব? ফার্স্ট হচ্ছে this represents the sum of, তার কারণ কি দেখো, from the triangle you can see the position vector R bar is equal to this vector plus this vector. সুতরাং আমরা এটাকে কি লিখতে পাচ্ছি? So I can write this is, say, representing, দাঁড়াও আমি একটু এমবিলিশমেন্টটাকে করে নিই. So this is R bar, এই টপের বারটা হচ্ছে because it represents the center of mass. আর যেহেতু এটা ভেক্টর, তাই এই ভেক্টরটাকে বোঝানোর জন্য আমি এখানে একটা ভেক্টর অ্যারো পুট করে দিই, this is vector. So it is R bar bar plus, then we have the other vector, we defined it by the rho, so I say this is rho bar, correct? So I call this as rho bar, correct? So this I just make a first bracket, correct? So this is our first bracket. So R bar thus is written as, the sum of these two vectors. Now is the case for V bar. What is the velocity? You see, what is the velocity of this arbitrary point? Now this velocity of the arbitrary point and the center of mass's velocity. I had, this is the center of mass's velocity. And I had, this is the particles, একটা arbitrary pointed velocity. So how these two velocities are related to each other? How these two velocities are related to each other? We know from our knowledge that this is nothing but, so I make a first bracket open here, make a first bracket open here, first bracket. So you see, I have this to be the sum of two velocity terms. So I'll be getting those two terms. Let me see. So one is the velocity of the center of mass, which I write it v bar. Barta manei hocche je this is center of mass, and since it is vector, I put an arrow on top of it. Plus. What is the case? Now, if at this instant, if I suppose that the angular velocity vector of the body is omega bar body, please see এগুলো সব কিন্তু আমাদের আগেই পড়ানো হয়ে গেছিল আগের সেমিস্টারে। হ্যাঁ, যে আগের সেমিস্টার না, আগের সেমিস্টারে, সরি, মানে সেকেন্ড ইয়ার ফার্স্ট সেমে আমরা পড়ি, হ্যাঁ সেকেন্ড ইয়ার ফার্স্ট সেমে পড়েছিলাম। সো এক্স্যাক্টলি, একদম ঠিক কথা। সো ইউ সি হিয়ার I write that, sorry, zero হয়ে গেল। So we see here, এই ম্যাথমেটিক্স এর ইকুয়েশনটা না লিখলে একটু মুশকিল, সেজন্য আমি লিখে দেখাচ্ছি। সো we see this is ওমেগা বার বডি, ঠিক আছে? আর এইটা একটা অ্যাঙ্গুলার কি বলে ভেক্টর বলে you put this. So you see therefore this cross, it requires to be crossed. What is the thing that will be equal to? It should be crossed with what? It should be crossed with this vector. So you see it's crossed with this vector. So ultimately therefore, please write it in your khata. Ultimately therefore, you see this integration is written like this. আমরা আজকে কেবলমাত্র, যেহেতু আজকে টাইম কম, আমরা কেবলমাত্র আজকে ফার্স্ট ইকুয়েশনটা জেনারেট করব, কারেক্ট? লিখে একদম পরিষ্কার লিখে। So we have, this is our integration, correct? So how this can be written? So let us write it again, once again. So তাহলে দেখো এখন জিনিসটা কি দাঁড়াচ্ছে। তাহলে if I distribute, প্রথম কথা হচ্ছে আমাকে এটাকে এই ভেক্টরটাকে ডিস্ট্রিবিউট করতে হবে ক্রস প্রোডাক্ট ইত্যাদি করে। So I can therefore say that কিভাবে আমরা ডিস্ট্রিবিউশনটা করব। So let's say ফার্স্ট আমরা এটাকে দিয়ে ডিস্ট্রিবিউট করব। So we take copy, paste it here, paste, cross, then we take this term, copy, paste, and write this integration চিহ্নটা আমি পরে দিচ্ছি। So dm so the whole thing needs to be integrated. আচ্ছা, আমি এখন না একটু তাড়াতাড়ি করবার জন্য আমি মাসটাকে আর তলায় লিখলাম না, বাট প্লিজ রিমেম্বার দ্যাট দিস ইন্টিগ্রেশন হ্যাজ দ্য ডোমেইন মাস। তার মানে এরকম তলায় এখানে একটা মাস তুমি তোমার খাতায় লিখে রাখো, প্লাস m। আচ্ছা, দেন উই হ্যাভ দিস copy, paste, then we take this cross product, sorry, copy, paste, then this term, entire term comes, paste, and just to make our reading different, মানে convenient, আমি এখানে একটা ফার্স্ট ব্র্যাকেট ঢুকিয়ে দিলাম, and then the whole thing is put under integration. তাহলে কি হলো, রোবার দিয়ে যে দুটো টার্ম ছিল সেই দুটো টার্ম হয়ে গেল। নেক্সট কামস প্লাস। আচ্ছা, আমি এখানটাতে যে পরের টার্মটা করব সেটাকে আমি জাস্ট কি করছি, আমি এটাকে মাইনাস করে লিখছি। সো মাইনাস, জাস্ট ভি বারটাকে আমি আগে দিয়ে, বিকজ ভি বার ইজ এ কনস্ট্যান্ট থিং, সো আই রাইট paste, then it will be integration of, so I write this integration sign and then take, you remember this was what? This was representing the just integration টাকে বোঝানোর জন্য আমরা জিনিসটাকে we take this format and then we have this r bar cross this one. তাহলে এইখানে what we find, আচ্ছা we make it plus, আচ্ছা please note যে দেখো, if I come to our this khata, this was your r bar, correct, and between these 2 points this position vectors is not changing because this is the center of mass, this is also a point. তাহলে in between this distance is not changing, so and it is not depending upon the other points also because it is not connected with the variable point. This is a fixed point, this is a fixed point, and that was a variable point. So in this integration actually the variable is this one, actually the variable is this fellow, not this. So as a result what I can say, I can take out this, bring out from this integration, and this integration will be therefore integration dm. So it is nothing but mass. So I put the mass m, and again just change this order of integration. আমি এটাকে লিখেছিলাম এই কারণের জন্য যাতে তুমি ইন্টিগ্রেশনটা বুঝতে পারো, সে কারণে আমি অর্ডারটাকে চেঞ্জ করে লিখেছিলাম। once I get this mass, now I change the integration once again, order of vector টাকে চেঞ্জ করে I take this as plus. জাস্ট তোমাকে বোঝানোর জন্য আমি এখানে অর্ডারটাকে চেঞ্জ করেছিলাম। now I again reverse it and make this, and then this integration goes out because I have performed this entire integration because other things were constant, so it is written in this manner. Now in a similar manner আমি যদি এবার লাস্ট টার্মটাকে দেখি তাহলে দেখো লাস্ট টার্মে কি রকম হবে। লাস্ট টার্মটা একটু তোমাকে মন দিয়ে দেখতে হবে, লাস্ট টার্মটা কি রকম হবে। so let's take the copy of it, copy, paste it here, then we take the cross product, then we open up the first bracket, this first bracket, make this part of the first bracket নিয়ে চলে এসো। এই now put the integration, কারণ আমি আগেই বলেছি তোমার ইন্টিগ্রেশনের ভেরিয়েবলটা হচ্ছে কেবল রো বার, কারণ এটাই চেঞ্জ হতে পারে। you can go on taking different such points on the body. so what is basically changing is this vector, তাই না? এই ভেক্টরটা তোমার চেঞ্জ হয়ে যাবে, এই ভেক্টরটা একই থেকে যাবে because you are considering the center of mass. so as a result we have this to be equal to rho bar. তাহলে এটাকে কপি করে এখানে বসিয়ে দিই, রো বার এই যাতা হলো এইখানে, and then you have this dn, right? so this will be therefore integration. Please note it in your khata. so ultimately what we get all these terms. now you see from here আমরা এখান থেকে কি পাচ্ছি তাহলে দেখো, first thing that we are getting is this আচ্ছা আমি বোধহয় একটা টার্ম বেশি লিখে ফেললাম না, 1 2 3 না ঠিকই আছে ওকে
ঠিকই আছে হ্যাঁ
ওকে সো নাও এইবারে এইটাকে দেখানোর জন্য দেখো এইখানে আমরা কি করছি, আবার আমাকে একটুখানি অর্ডারটাকে চেঞ্জ করতে হবে। আমি কি করলাম, এই ভেলোসিটি ভেক্টরটাকে বাইরে নিয়ে গেলাম, এই ক্রস প্রোডাক্টটাকে বাইরে নিয়ে গেলাম, and put a minus sign here. তাহলে তোমার ইন্টিগ্রেশনটা থাকলো কি খালি এটা, তাই না? আচ্ছা এইবার তুমি খেয়াল করে দেখো এই ইন্টিগ্রেশনটা কি, রো বার dm over the mass m. this represents the mass, this is rho bar dm. তাহলে এই রো বার dm টা কি রিপ্রেজেন্ট করবে, এই রো বার dm টা রিপ্রেজেন্ট করবে, দেখো এখানে চলে এসো, রো বার dm টা কি রিপ্রেজেন্ট করবে, this will be equal to mass times total mass of the body. ইন্টিগ্রেশন আবার বলছি, এই যে ইন্টিগ্রেশনটা, লেটস সি দিস ইন্টিগ্রেশন, এটাকে একটু আলাদা করে তোমার জন্য তাহলে তুলে নিয়ে আসি। কপি, সে আই রাইট ইট হিয়ার, I paste it here. What will be this? This will be equal to mass times we have a mass into the position vector of the center of mass with respect to the center of mass. This is nothing but position vector of the center of mass with respect to the center of mass. তাহলে কি হবে সেন্টার অফ মাসের রেসপেক্টে সেন্টার অফ মাসের পজিশন ভেক্টর কি
নাল ভেক্টর হবে নাল ভেক্টর হবে
নাল ভেক্টর কারেক্ট অ্যাবসলিউটলি কারেক্ট তাহলে কি হলো this result is becoming a null vector so this result does in your khata please note that this is the integration that you have তাহলে দেখো এবার কোথায় কোথায় সেই ইন্টিগ্রেশনটা তোমার আছে you see this term is having this integration correct এই দেখো আমি যেখানে হাত নাড়াচ্ছি এই জায়গাটায় সরি this term এই জায়গাটায় সেই ইন্টিগ্রেশনটা আছে আর কোথায় আছে এখানে আছে সো all these terms তার মানে কি এই পুরো টার্মটা দেখো লাস্ট টার্মটা পুরোটা নাল হয়ে গেল বিকজ ইট ইজ নাল ভেক্টর হিয়ার আবার এই টার্মটা পুরোটা নাল হয়ে গেল তাহলে ইট উইল বি আলটিমেটলি কি দাঁড়ালো ইকুয়াল টু হোয়াট আলটিমেটলি দাঁড়ালো দেখো দিস তাহলে আমি ইন্টিগ্রেশনটাকে কপি করে নিই তাহলে কি দাঁড়ালো জিনিসটা গিভ মি সাম টাইম সো দিস ইজ কপি দিস ইজ পেস্ট সো এটা পেস্ট হয়ে গেল এখানে সো ইট ইজ রো বার ক্রস ওমেগা বার বডি ক্রস রো বার ডিএম প্লাস কি থাকলো এই জিনিসটা কি না এইটা দিস ইজ হোয়াট দিস ইজ কপি পেস্ট এইবার আমি বলবো নাও ইউ লুক এট দিস টার্মস ভেরি কেয়ারফুলি look at these terms very carefully now first I like to take your attention over here what does this integration is representing you see this represents omega bar body তাহলে আমরা একটু চলে আসি এখানে this is what this is omega bar body cross rho bar body is nothing but the relative velocity of this point with respect to the center of mass this omega bar body abar bolchi omega bar body cross rho bar this represents the relative velocity why it is relative velocity দেখো এই টোটাল ভেলোসিটিটা ছিল this was the velocity এটাকে আমি যদি কপি করে নিয়ে এখানটায় বসাতাম একটু গ্যাপ দিয়ে একটু গ্যাপে হ্যাঁ একটু আমাকে সময় দাও এই জায়গাটাতে now had I put here this velocity vector কোন ভেলোসিটি ভেক্টরটা এই ভেলোসিটি ভেক্টরটা তাহলে এটাকে কপি করে এখানটায় বসিয়ে দাও this should be equal to this তাহলে আমরা দেখছিলাম এই ইকুয়েশনে আমি যদি this minus this করি তাহলে সেটাই কি রিপ্রেজেন্ট করবে the relative velocity because this is observer's velocity এটা কি অবজেক্টের ভেলোসিটি object velocity is equal to observer velocity plus relative velocity so ultimately this represents the relative velocity term. So what you are saying, the relative velocity multiplied by the mass giving you the relative momentum and you are taking the moment of that relative momentum. তাহলে তুমি এখানে কি করলে এই যে দুটো ভেলোসিটিকে তুমি যদি তফাৎ করতে you would have got a relative velocity term that relative velocity term would be perpendicular to this vector এই ভেক্টরটার সাথে পারপেন্ডিকুলার হতো তাই না তাহলে কি হচ্ছে যেটা now this relative velocity term gives you the এবার যদি আমি এটাকে টোটাল ইন্টিগ্রেশন করি this will give you the relative angular momentum with respect to your center of mass তার মানে এইটা is nothing but the relative angular momentum with respect to center of mass এবার তুমি জানো তোমার আবার সেই পুরনো নলেজ থেকে যে সেন্টার অফ মাসের রেসপেক্টে রিলেটিভ অ্যাঙ্গুলার মোমেন্টামও যা absolute angular momentum hota tai in place of this I can write in place of the first this আমি এটাকে relative absolute কিছুই বলবো না আমি খালি বলবো হচ্ছে কি this is the angular momentum with respect to the center of mass sorry the center of mass I define it by the symbol c আমি এটাকে just চট করে সাবস্ক্রিপ্ট করে দিই so this is this plus থাকবে কি this term this is what this is the moment of sorry এই তাড়াহুড়ো করতে গিয়ে বিপদ হয়ে গেল undo so this is copy control c আমাদের টাইম প্রায় হয়ে এসেছে control v so this ultimately what I get from here I get the equation that আমি দেখো একদম যদি লাস্ট লাইনে আমি ইকুয়েশনটা নিয়ে আসি তাহলে the equation becomes equal to what now this becomes equal to this is the angular momentum about any arbitrary point So angular momentum about any arbitrary point. So make it copy. আমি তোমার এই খাতাতে নিয়ে চলে এলাম, জাস্ট এখানটাতে নিয়ে, সরি, জাস্ট আমি এখানটাতে কন্ট্রোল ভি করে দিই। So you see this equation, একটু বড় করে দিই ইকুয়েশনটাকে যাতে তুমি ভালো করে দেখতে পারো।
Sir, I think we should stop here.
ওকে ওকে, তাহলে আমরা এই অবধি রাখি, আমরা নেক্সট দিন না হয় এর পরের থেকে স্টার্ট করব। সো জাস্ট সি দিস ইকুয়েশন, উই উইল ডিসকাস in our next class from this equation. We will explain what are the terms that we are getting. Okay, thank you.
এটা কি স্যার সিওএম এর
সি হচ্ছে সেন্টার অফ মাস অফ দা বডি। আমরা এটা নিয়ে আবার পরের দিন মানে কালকে আমরা আবার এটাকে নিয়ে ডিসকাস করব। তোমরা খাতাতে ইকুয়েশনটা খালি লিখে রাখো। আজকে টাইম হয়ে গিয়েছে, ঠিক আছে?
ঠিক আছে স্যার।
Okay, sir. Okay, sir. Thank you, sir.
Okay, thank you.
ঠিক